So, 2016 10A, first thing, standard question, distinguish between a strong acid and a weak acid. Now, when they don't differentiate whether we're going to talk about Bronsted Lowry or Arrhenius, discuss both. So, a strong acid, according to Bronsted Lowry, that's the easier one. I'd be saying there it's a good proton donor. Talk about both. And also, according to Arrhenius, it fully dissociates into your hydrogen ions. What is that yellow thing? I have no notion. A weak acid, on the other hand, is a poor proton donor, just the opposite. And only slightly dissociates. That's why they're given them Ka values, the degree of dissociation into hydrogen ions. Now into the meat and two veg. Calculate the molarity of sulfuric acid that has a pH of 2. Now, anywhere I see pH, what I do is pH is equal to the negative log to the base 10 of the hydrogen ion concentration. So if anyone knows why that is doing that, you can let me know. So now fill in. It's got a pH of 2. So 2 is equal to minus log to the base 10 of your hydrogen ions. Bring across that minus. So minus 2 is equal to the log to the base 10 of your hydrogen ions, and either use your anti-log or your Liverpool beats Newcastle powerful. Remember your base to your power. I just like that way because you're going to be using it in maths anyway. It becomes familiar. And when you put that in your calculator, so shift and log gives you your anti-log. Just remember to put in a minus before the pH, 1 over 100 or 0.01. Now we haven't technically answered that. Now sulfuric acid alarm bells should be ringing every time we do sulfuric acid, because sulfuric acid is this thing known as a dibasic acid. So H2SO4, strong acid, and it breaks down into 2 hydrogen ions because of its conjugate base also being a weak acid itself, plus SO4 2 minus. Now at this stage, what determines the pH, the power of the hydrogen ions, is the hydrogen ions. So that is 0.01. We want to work out the molarity of H2SO4, and if you look at the ratio, it's 1 is to 2. So divide that by 2, and we get 0.005, or 5 by 10 to the minus 3. Whatever answer you want is the molarity there of your sulfuric acid. So a tight wee question, but again, once you see pH, what's the other way of writing it? Now, the thing I hate about maths, that's like the first bit of part 2. There's another bit of part 2 here as well. The acid dissociation constant for a weak acid is 1.8 by 10 to the minus 4. So Ka is equal to 1.8 by 10 to the minus 4. Calculate the molarity of a solution that also has a pH of 2. Now it's monobasic actually, so we don't need to divide it by 2. So if we did the anti-log of a pH of 2, we're going to end up with the same answer as we had initially with our sulfuric acid. So the hydrogen ions is equal to 0.01. Now think what's in our locker for the weak acids. The only thing we got is our pH formula and also our hydrogen ion concentration represented by gamma, Ka times Ma. Now we know the hydrogen ion concentration is 0.01 from here. Because it's monobasic, we don't need to divide by 2. Square root of 1.8 by 10 to the minus 4 times it by the molarity, which we're working out. So you can call it Ma or M or X, whatever you want. Clive. Now, how do you get rid of the square root? You square both sides. So this is testing your maths. And that is just a brute of a number, that 1.8 by 10 to the minus 4. To work out what M is, divide and below by it. And then throw that all into your calculator. And you get 5 over 9 as the molarity. It's going to be a woeful looking decimal, or 0.56, say. And that's it, the molarity of that weak monobasic acid. And then in part 3, to find Kw. Jeez, I didn't spread this one out so well. Kw. So in part 3, Kw, the ionic product of water, it's a product of the molar concentration of hydrogen ions times the hydroxide ions, sorry, that should be a minus, in water. So you can put that in words as well. So the product, because it's being multiplied, the product of the molar concentrations of hydrogen ions times hydroxide ions in water. So put in the, if you wish, the equation format, and then throw in the words, because the equation gives you the words. The value of Kw, like all these equilibrium constants, is temperature dependent. And at 59 degrees Celsius, Kw is equal to 9 by 10 to the minus 14. What is the hydrogen ion concentration in pure water? Now, pure water simply means that the hydrogen ion concentration is the same as the hydroxide ion concentration. That's what determines it's pure. And it's one of the limitations of your pH scale is that it's temperature dependent. So we're using our previous answer like you do in maths a lot of the time. So instead of writing Kw, we know that's expressed as H plus times OH minus is equal to 9 by 10 to the minus 14. They're the same because it's pure water. So you can call them both H's if you wish, or a lot of the time in the maths, it makes it easier, is your X's. Now we're flying around the pig's back. X squared is equal to 9 by 10 to the minus 14. To work out X, it's the square root of that tiny number. And X is equal to 3 over that, or 3 by 10 to the minus 7. Therefore, technically, they said, what is the hydrogen ion concentration? The hydrogen ion concentration is 3 by 10 to the minus 7. So that's your 2016 one. Calculations, and working through most bits. Next one we'll look at is 2014, question 7. So nitrous acid is a weak acid that is readily oxidized to a strong acid, nitric acid. So, distinguish between a strong acid and a weak acid according to Bronsted-Lowry. So once again, a strong acid is a good proton donor and a weak acid is a poor proton donor. So then we theory bits should be full marks. Nitrous acid dissociates in water according to the following. Identify the two substances acting as bases. Now bases are proton acceptors. So if we're going from left to right, HNO2 changes into NO2 minus. So it must have given away a H plus. So that is known as, my HNO2 is known as my Bronsted-Lowry acid, whereas H2O is my base. Just to save a wee bit of time, I think you should be good enough at this. My base is H2O. It's my Bronsted-Lowry base. Now I'm going from right to left. Which one gives away the H plus? It's your H3O plus. So that's known as my conjugate acid. And my conjugate base, the proton acceptor, is NO2. So there's my two answers. Your nitrate ion, NO2, and your H2O, your water. See now, into the difficult sort of things. Define pH. pH is defined as the negative log to the base 10 of the hydrogen ion concentration. Put it in words as well. You can get it from the formula, get it from the equation. The negative log to the base 10 of the hydrogen ion concentration. The pH of a 0.2 molar solution of nitrous acid. Now nitrous acid, they told us at the top, is a weak acid, so it's not going to fully dissociate, is 2 at this temperature. Calculate the H3O plus ion concentration in moles per litre. As is a weak acid and it's monobasic, it's not going to be 0.2. If it's a strong acid, it would be 0.2, but since it's a weak acid, it only slightly dissociates. So we're going to have to use the pH that they give us there. So the pH is 2, your negative log, the base 10 of your hydrogen ion concentration. Bring in that minus. And then do your anti-log, or your Liverpool beats Newcastle, powerful. So your base is 10, the power is minus 2. There's my hydrogen ions. 0.01, but your shift, log, minus 2, 1 over 100, or 0.01 molar. So there we can see it's a weak acid because the 0.2 molar only slightly dissociates to produce 0.01 moles per litre of hydrogen ions, despite the fact that it's a monobasic acid, in which it should be 1:1. So the concentration, that's the first answer there. Because again, I don't like the way they've split this up. I'm going to say this here is C part 1. There's C part 1 done. Part 2. Explain clearly how this hydrogen ion concentration, or your H3O plus, your hydronium ion concentration, confirms it's a weak acid. It confirms it as 0.2 moles per litre of your nitrous acid dissociates to give 0.01 molar hydrogen ions. Despite, I may as well since I know it, despite the fact it's a monobasic acid. And by that I mean it should be a 1:1 ratio. Strong acids would fully dissociate. Why not? Stick it all down. To give 0.2 moles per litre of my hydrogen ions. You know, whatever you know, stick it down. Part 3. What concentration of nitric acid would have the same H3O plus ion concentration? So, in this one, what concentration of nitric acid, okay, would have the same H3O plus ion concentration? Gee, wee bit wordy there. Now, my hydrogen ion concentration, or my H3O plus ion concentration, was 0.01 molar. Now, nitric acid, HNO3, is a strong acid, so it fully dissociates. So if I had 0.01 molar of H plus or H3O plus, I'm going to have the equivalent concentration of my nitric acid. It's a 1:1 ratio. So your answer there is simply 0.01. And then your last bit, calculate the hydroxide ion concentrations of both of these acidic solutions. Now they're both the same. Now, from the ionic product of water, Kw is equal to the hydrogen ions times your hydroxide ions. Now at 298 Kelvin or 25 degrees Celsius, in which it mentions there, Kw is equal to 1 by 10 to the minus 14. We know the hydrogen ion concentration is 0.01. We just have to work out your hydroxide ion concentration. And that's just like an x. So again, if I had 2x equal to 8, how do I work out x? Divide by the number stuck on. So here, my number stuck on is 0.01. So it's 1 by 10 to the minus 14 over 0.01. And when I put that into my calculator, I get 1 by 10 to the minus 12. Lovely. Which is a really small dissociation of my hydroxide ions, which makes sense as it is an acid. That's that one done. The remaining bit of that question was your test for your nitrates, like in water as well. And then your last one there, 2011 question 7. Sulfuric acid is a strong dibasic acid. The formula HA represents a weak monobasic acid. How do strong acids, so this every year they ask this, strong acids differ from weak acids in their behaviour according to Arrhenius. So discuss both. So strong acids fully dissociates into hydrogen ions, weak acids only slightly dissociate into hydrogen ions. And according to the Bronsted-Lowry theory, strong acids are good proton donors, weak acids are poor proton donors. Easy, it should be the full 12 marks there. Now, the second bit. What is a conjugate base of sulfuric acid? Now, sulfuric acid is H2SO4. Conjugate acids my go-to. When I ask for a conjugate acid, A for acid, A for added. So here for my conjugate base, instead of adding on a H+, I'm taking away a H+, and what I'm left with is HSO4-. And the second one there, the conjugate base of HA, similar story, take away a H+, and I'm given A-. Which of these conjugate bases is stronger? So this goes back to the fact that the stronger the acid, the weaker its conjugate base, or the weaker the acid, the stronger the conjugate base. So which one is stronger is A minus, as weaker acids give stronger conjugate bases. Explain by giving a balanced equation for its dissociation in water that the conjugate base, which is our HSO4 minus, the conjugate base of sulfuric acid is itself an acid. Explain by giving a balanced equation for its dissociation in water. Jeez, that's wordy. So I've got the conjugate base, HSO4 minus, its dissociation in water, H2O. It's an acid, so it's going to be a proton donor, according to Bronsted-Lowry. And what you're left with is SO4 2 minus plus H3O plus. So that's it done. It's tough. And now D there, define pH, give your equation, and then your words. It's defined as the negative log to the base 10 of the hydrogen ion concentration. I'll say that's D part 1. D part 2. Calculate the pH of a 0.2 molar solution of weak acid HA, the value of whose acid dissociation constant is that. Now anything with the weak acids, we've got the pH formula, and in order to determine the pH, we need our gamma. So what are we looking for? We know its molarity, it's 0.2 molar. We know its acid dissociation constant. So we're going to work out the hydrogen ion concentration first of all, and then throw that in to the formula up here. So it's the square root of 6.3 by 10 to the minus 5 times that by the molarity, which is 0.2. Throw it all in. Oh, cripes. So H plus there, 3.55 by 10 to the minus 3. Not that bad. And now to work out the pH, negative log to the base 10 of your hydrogen ion concentration, minus log to the base 10 of that monstrosity. And now I have to go as minus, it comes up answer minus, delete both of them, minus log to the base 10 of your answer, and we get 2.45. 2 decimal places, I think it's lovely, 2.45. Is that what your digital pH meters would read? And part 3. What is the concentration of sulfuric acid that is the same pH? Now the pH there, we worked out to be 2.45. Substitute in the formula that we know for this. It's the negative log to the base 10 of the hydrogen ion concentration. Now things start piecing together. Bring across that minus. Do your anti-log, or do your Liverpool beats Newcastle powerful. Log base number power. So base always goes to a power is equal to the number. Throw that in our calculator. So the shift log minus 2.45. 3.55 by 10 to the minus 3. And they've asked for the concentration of sulfuric acid. Think about sulfuric acid. It's one of these ones, alarm bells should be ringing. It's a dibasic acid, so it splits up into that. We know its concentration there is the 3.55 by 10 to the minus 3. What's the ratio? 1:2. So how do we go back to work out the concentration of sulfuric acid? We divide it by 2. So 3.55 by 10 to the minus 3 all over 2. Answer, divide that by 2. 1.77 by 10 to the minus 3. And that's it.